All right, so you guys are just going to be taking these on your own sheet of paper. All right, so go ahead and title it Equilibrium. We're going to kind of keep adding to these, so if you want them in a journal, that's fine, wherever you take notes. So title it Equilibrium. What is the big thing in a lot of these equilibrium questions that was different from what we've seen in the past? What's like a big thing that stands out to you?
Arrows point both ways.
Right, the arrow pointing both ways, definitely. So you'll see it like that, or you'll see it like that. Just depends on what who's drawing it, okay?
Energy.
No, energy we've seen. But, anything else?
What if it's the other way?
What if it's the other way? What do you mean, what if it's the other way?
Like that and like that.
You're talking about the top one?
Yeah.
No. Because they don't go nicely.
Oh, so it doesn't mean anything?
No, that's just the way Miss Vogel does it. It's a good question. All right. Okay, so equilibrium we know is something that is going in the forward and the reverse direction. What is the key point though? Those things are happening at what? At the same time. Okay, so we're gonna take it one step further and we're gonna say at equal rates. Okay. So equilibrium means at equal rates, forward and reverse is happening. I'm going to put RXN, that just means reaction. Okay? At equal rates, forward and reverse reactions are happening. Okay, and we've seen that according to Le Chatelier's principle, that's what your whole POGL was about. And we'll take official notes on those later, not today. Okay, but we've seen according to his principle that if we change a condition, it's going to force one of these rates to possibly happen a little bit faster than the other in order to reset this fabulous little equilibrium. Okay, so I want you guys to see this quick little video clip from Bozeman. I'm only gonna let you watch like 30 seconds of it because you don't know what Q is yet. So we're just gonna watch the way he talks about this. Let me see if I'm gonna be able to. Yeah, there we go. All right. Let's see if I can get this to work. Is it going? Not yet? No?
Also calculate Q.
All right, just listen.
The concentration of products to reactants at any given time. And over time, Q.
That is circled. Yep, you do not need to write the top part because I feel like we've already established that. Okay? So dynamic equilibrium is just a situation in which two or more processes occur at the same rate so that no net change occurs. So you guys just need to say two processes occurring at the same rate, no net change. What no net change means is that you looking at this thing with your naked eye don't see anything else happening. Okay? And with your glasses, you still don't see anything happening. Okay? Because they're happening at those equal rates. So again, all you have to write is the stuff underlined in pink. Okay. So from his little video, this happened once that ball reached the bottom of the little ramp looking thing, okay? All right. Ooh, just kidding. It is a lot of stuff, yep. All right. So for your general equation, I do want you to write this, okay? All right, so your general equation is little a big A plus little b big B, a forward backward arrow, and then C, C, D, D. All right? What that's showing you is those little letters are your coefficients. Big letters are the different chemicals, I guess you could say. All right? You always write it in that forward direction, whatever way it's starting. Okay? For y'all, as much as you guys are going to do. Okay? So these will always be the reactants on the left. Those will always be the products on the right. Even when it starts going reverse, you're not going to reverse your products and reactants, okay? You still treat them the same way, and you'll see why in a second. So your general equation is that. You might not have that many products, might not have that many reactants. But what you guys are going to be responsible for is I'm going to give you something like that, and I'm going to ask you, hey, write down your equilibrium expression, okay? Yeah, there you go. All right. You're going to write down your equilibrium expression. Now, this part over here to the right, I'm sorry, to the left, right there, that's just telling you that brackets mean molarity. You guys remember doing that last chapter, okay? Brackets just mean molarity, so if you need to write that, please do. The rest of it, I feel like, is pretty self-explanatory. So your equilibrium expression defines your equilibrium constant, okay? There's not one set constant. It just depends on your reaction and the conditions, okay? So Kc is equal to, if you notice, C to its what? Coefficient. And then the D to its coefficient, all over A to its coefficient, B to its coefficient. So if you notice in summary, this is products over reactants. Do you guys see that? And that's why it's going to be important that don't just go switching things just because it's going in the reverse. It is still products over reactants because that's going to mess with your little equilibrium constant. Yeah. You're always going to do that. Yep. And basically what that comes down to is what you guys did in your POGL with the shifts and stuff like that. You're going to see it's not necessarily the K value. K is once equilibrium's established. But when he was talking about, I told you guys you don't know what Q is. Q is going to talk about when it's not at equilibrium. And so that Q might have more products than reactants, or it might have more reactants than products, and it's going to have to shift in order to find that K value, or equilibrium. You guys won't have to do that. That's AP stuff, okay? I just need you guys to understand that this is an expression. You guys need to fill out your own and solve for K. That's as much as I'm requiring from y'all, okay? All right. So, one other thing. Please put a little note off to the side that says, never, never, never include solids, liquids, and for the most part, water, okay? Exception. In your little POGL you just did, you have gaseous water. That one did matter, okay? It was one of the main characters. Especially when you get to acids and bases, water is kind of like the one that's standing on the side.
Wait, where are we never including these?
In the expression. So, if your guys' chemical equation consisted of a solid breaking into pieces and being aqueous, you would never include the solid. You would only put the stuff that's aqueous. Does that make sense?
So we're not going to put all of our reactants in the equation?
Correct. If it's solid, liquid. Because these guys basically aren't going to change with concentration.
What if everything has a solid?
Then you don't have, then there should be no reaction happening. Think about it. Can a solid react with a solid and just make a new solid? Okay. All right. I'd like to see that. Go ahead and research that and let me know where it is. Thanks.
Is it water in any state?
Gaseous you usually include. Okay. Gaseous, it most likely is acting as a character, but that's only when you're dealing with pressures. So for y'all's purposes, I won't do that to y'all. Okay? All right. All right, and do you guys know what I mean by liquid, by the way? What's the difference between liquid and aqueous? Aqueous sounds cool. All right, aqueous means that it's a solution, means something was dissolved in water. So that means that ions are split apart. There's stuff going on. Liquid means that I either melted something, so it's a pure substance, or it's water, just plain old water, nothing going on. All right. So because of that, does concentration of something, if it's just melted, matter? No, right? It's 100% that, right? So the only thing we care about are things that have those varying concentrations, which would be your aqueous stuff.
Okay. So like if I took like.
All right. I do want you do not need to draw anything but the y-axis, x-axis, and then the two lines, and label the top one as reactant, the bottom one as product. Okay? Make a little sketch, does not have to be big. I just need you to not freak out when you see this graph and I'm asking you, hey, who does the top line represent? Okay? So you'll see this one is a reaction rate graph. Yeah, if you notice the reaction rate is on the y-axis. This could be a concentration graph, and it's going to look really, really similar, because what you're seeing here is, let's just pretend it was concentration, right? This is concentration means you have a ton of reactants, and they're all running out. You have no products they're making until they reach equilibrium, all right? And it's very similar. And I think the concentration one is a little easier for y'all to grasp than rates, but it's the same idea, okay? So just draw a little sketch of the graph, do time, reaction rate, and a little curvy. They meet up, they go equal.
Oh, do the curvies?
Do the curvies, definitely. And say reactant is the top one, product is the bottom one.
They're on top of each other.
I'm sorry?
When they meet up, like, it's like one line, you just made it.
It can be two. But don't worry about that. Actually, you know what? For this graph, yes, they have to meet up because it's a rate, right? Concentration, you'll see that line kind of split, and they just stay at a set concentration. So. All right. Okay. So after equilibrium is attained, the concentrations of the products and reactants remain constant. So a ratio of their concentration should also remain constant. Okay? I don't really need you guys to write that. Do you guys understand what it's saying? Things kind of just hit this constant thing, and that's your equilibrium. Okay? So that, well, there's the answers. All right. So if KEQ, by the way, is just that KC that I made you guys do, okay? KC is specific to concentrations. KP is for pressure. KEQ is like the general one. Then there's KW, KA, KB, KSP. I think I got them all. 7. So you guys will not have to do that. You guys get this one. That's it, okay? You're going to say if KEQ is greater than 1, are the reactants or products favored? Yes, because it's circle. But yes.
The arrow's pointing that way, and that's the product side.
Oh, that's another way to think of it. That's cool.
Yeah, it's like that.
That's cool. But what I need you guys to actually grasp is this. Look at that. Okay. If we said that K is products over reactants, and we're saying that we have something that's bigger than 1, so let's just say my answer is 5, right? Who did that mean you had more of, your products or your reactants? You had more products, therefore products were favored. So is that the forward direction or the reverse direction? Forward. It means the forward one is happening faster. I'm making more product. Okay? Yeah. Can I go like that? Is that cool? All right. Put the opposite one on there as well. If KEQ ends up being less than 1, then you can tell me that the reactants are favored. So the reverse one. is more apt to happen because you have a bigger number on the bottom. If it's like 0.1, which you guys will actually see is like 1 times 10 to the negative 15 or something like that. And that has to do with solubility, okay? So I really need you guys to grasp this because when I bring in how it relates to your solubility, what you're going to see is all those things that we said were insoluble are kind of soluble. They're like a little bit, but they have different K values. And so, question, if my K value is tiny, like super tiny, is that a very soluble substance? I want you to think about that for a second.
Yes.
How does this stuff even relate to solubility?
So what I just said, so I want you guys to think of this, okay? So if I had this guy, and we're just seeing if he can split into this, right? Do you guys agree that's soluble? That's what that's kind of showing? All right. But if I have more reactants, is that a very soluble substance? No, it's staying intact. So a small, so add this to your notes. Small, just hold on. Small KSP means insoluble. And that'll be the last thing we're writing, okay? Because I'm going to connect it to your solubility rules tomorrow. Huh? KSP is specific to a salt breaking into its pieces. So don't worry too much about it yet. Just write that. Okay? Yeah, and then a big KSP means that it's more soluble. So all your things that were insoluble kind of have their own rankings as well. And that's what I'm going to show you tomorrow in the warm-up.
But you just said that if it was, I get this, big, it was going to be harder to...
Wrong. If it's big, it means you have more products. You have more splitting. So it's soluble. It does. Okay.